Welcome to the Explainer. Today, we are executing a rigorous, entirely fluff-free technical teardown of the Notion 3.4 and Spring 2026 architectures. Setting all of the marketing speak aside, our focus is strictly on backend optimizations, system engineering, and the fundamental structural shifts required to actually support a deeply integrated AI core.
Here is our architectural blueprint for today. We will systematically cover database optimization, AI routing and economics, autonomous agents, external orchestration via NCP, and finally, enterprise security. Let's dive in.
Part 1. Database optimization and data architecture. Let's start with the fundamental data structures.
Initial page render times have officially improved by 28%. This is an absolutely critical metric. By accelerating client-side DOM hydration, the hardware load is directly reduced on the user's end. In previous iterations, loading heavy tables packed with thousands of linked records would severely bottleneck the main JavaScript thread in the browser. Now the client device no longer spikes its CPU just to process these visual nodes. The updated interface actively avoids thread blocking during complex relational queries. For operators working with massive datasets, this prevents input lag and ensures continuous, unblocked performance.
Beyond render times, architectural bloat has been aggressively stripped right at the schema level. Historically, if you wanted to format aggregated data like currency or percentages, engineers were forced to build secondary formula columns strictly for visual output. That approach heavily bloated the database schema and spiked computational overhead during the rendering of complex relational tables, simply because the client had to parse an entirely separate layer of logic. Now, native rollup formatting applies directly at the aggregated property level. This entirely purges those redundant formula layers and streamlines the schema. By eliminating these secondary calculations, CPU overhead drops drastically when extracting, indexing, and displaying interconnected data. These rendering optimizations carry directly into navigation and payload efficiency. Hovering over a breadcrumb now reveals sibling database pages without triggering a full-page load. This drastically reduces heavy server requests and expensive database queries during deep tree traversal. Furthermore, by isolating tab display customizations to the local client and allowing the global muting of irrelevant discussion threads, the system deliberately restricts computational noise. It only renders the exact required UI state. For network engineers, this means conserving massive amounts of bandwidth and server-side rendering resources, ultimately delivering a significantly lighter payload to the end user.
Moving up the stack to Part 2. AI routing and token unit economics.
Agent operating costs have been slashed by 35 to 50% across the board. This completely alters the fundamental unit economics of enterprise AI. It shifts the entire dynamic from a CapEx discussion to an OpEx discussion. When your computational overhead drops by half, running continuous background AI operations transitions from being a highly experimental luxury to a totally viable component of your core infrastructure. Mass data processing and high-frequency background triage can now be pushed entirely onto automated rails without breaking your enterprise API budget or triggering strict rate limits.
This massive cost efficiency is driven by strict, dynamic back-end routing logic. We're looking at a definitive bifurcation in model deployment here. Heavy cognitive models, specifically Claude Opus 4.7, are strictly sandboxed for complex reasoning tasks, which yields 3 times fewer tool calling errors when absolute accuracy is paramount. Conversely, routine extraction and data pipelines are dynamically routed to high-speed micromodels like GPT 5.4 Mini and Haiku 4.5. Because these micromodels consume up to 10 times fewer credits per execution, this architecture perfectly balances deep analytics with sheer computational throughput. You are maximizing utility for every single dollar spent.
Part 3. Autonomous agents as scalable microservices. Let's look at the active components.
Real-world enterprise deployments prove this architectural shift is already happening. RAMP utilizes a specific agent to instantly extract go-to-market assets. Clay completely replaced their Tier 1 internal IT support with an automated resolver. BrainTrust deployed an autonomous competitive intelligence parser that continuously updates internal documentation based strictly on external market signals. These are no longer passive chat interfaces waiting around for a user prompt. They are continuous operational daemons running actively inside the workspace, fundamentally replacing static scripts and outdated manual data entry protocols.
The deterministic nature of this background execution pipeline is absolutely paramount for system integrity. It operates in 3 highly rigid phases. First,
Ingestion, safely parsing unstructured context from external platforms like Slack, Box, or Salesforce. Second, semantic application, applying programmable, hard-coded operational logic to accurately format or categorize that ingested data. And third, execution, direct DOM mutation. The agent natively alters the document or database structure on its own, completely bypassing volatile clipboard buffers or manual cursor emulation. This totally eliminates the race conditions and data corruption risks we typically associate with legacy automation tools.
This brings us to AI Autofill, which fundamentally alters database state management. Database enrichment is no longer a synchronous process that freezes your UI while waiting for an API response. Instead, it operates strictly as an asynchronous, continuous background cron job. It continuously extracts, enriches, and categorizes raw data entirely on the server side. For system architects, this guarantees absolute data consistency at scale, and it does so without ever requiring a manual trigger or locking up the user's workspace during heavy, complex database enrichment cycles.
Ascending to the integration layer, Part 4. External orchestration via MCP. The Model Context Protocol, or MCP, is a standardized, highly secure bridge. It radically upgrades AI models from being read-only entities into active initiators of external actions and cross-platform API calls. For engineers and system architects, MCP is the definitive gateway. It completely transforms what was once a static workspace into an active system-to-system orchestrator fully capable of securely pushing complex state changes out to your entire external technology stack.
By piping these internal agents through platforms like NAN using MCP, your workspace practically upgrades into a central command node and webhook orchestrator. Concurrently, programmatic API access now exposes full meeting transcripts and generated telemetry. You can now architect pipelines where an AI natively parses a massive meeting transcript, synthesizes the core action items, and immediately utilizes MCP to push fully formatted automated JSON payloads directly into external trackers like Jira. Zero human intervention required. This is complete pipeline automation, ensuring absolute state synchronization between your workspace and your external development environments.
Finally, Part 5. Enterprise Security and Permissions. Let's look at the necessary guardrails.
Under legacy architectures, allowing an external user or an automated system to add a database record often required handing over broad read and write access. That inherently exposed adjacent database rows to potential scraping or unauthorized auditing. The new Can Create Pages permission enforces a strict append-only isolation. This is an absolute technical necessity for this kind of automation. It allows external contractors or automated ticket logging systems to blindly write new data into a unified database without ever exposing the underlying, pre-existing database states or internal analytics to unauthorized entities.
At the identity and compliance layer, the platform enforces strict enterprise standards, featuring SAML-based SSO and SIM for highly automated user lifecycle provisioning. Crucially, as these AI agents gain access to parse private Slack channels, the ingestion process is governed by rigid role-based access control. The AI is structurally blocked from bypassing legacy permission trees. This guarantees that context leakage between distinct departments or across different security clearance levels is cryptographically impossible. On top of that, deep system auditing logs every single cross-platform action executed by these agents, maintaining your strict enterprise compliance and overall security posture.
Given the seamless integration of the Model Context Protocol, the deployment of asynchronous background cron jobs, and the drastically optimized unit economics of these micromodels, the very boundaries of internal tooling have fundamentally shifted. It is time to seriously evaluate your infrastructure. Are you still designing a static document repository? Or is it time to rethink your internal paradigm and architect an AI-orchestrated operational core? The underlying architecture and the structural security are now firmly in place to support the latter. Analyze your enterprise workflows, leverage these structural updates, and optimize your systems.